All right, folks, I do want to welcome you back to Unit 10. This is thermochemistry. If you are a pre-AP student, if you're doing pre-AP chemistry with me, I think it's okay for you to skip this one. It's not going to be a very long screencast, but it's really intended for AP students. So if you are a pre-AP student, just go on ahead and skip this one and move on to the next one, and I'll meet with you at later on. If you're an AP student, let's go. So here we go. What I want to talk about briefly is using something called heats of combustion to calculate the heat of reaction. Now we all know the heat of reaction is this, it's delta H. So we're looking for the delta H for a particular reaction. And we're going to use something called heats of combustion. Now what does that mean? Well, let's take a look at a specific reaction. We have CH3OH, that's methanol in the liquid form, forming 8COH plus H2 gas, and we want to know the delta H for that reaction. All right? So how would we go about that? Well, we've looked at Hess's law, right? But Hess's law requires that we have certain basic reactions that we know that the delta H's for those reactions that can be manipulated, flipped or doubled or whatever the case may be. But what if we don't have those given to us? Well, another way to do this procedure to find the delta H is to look up, and this is for organic molecules. This is for molecules that involve hydrogen and oxygen and carbon, obviously. But we can use something called heats of combustion. Now, what is combustion? What do we mean by combustion? Well, we mean burning in the presence of oxygen, right? So if we have a hydrocarbon like CH3OH, we can burn it in the presence of oxygen, right? So what I can do is I can look up the heats of combustion for all three of the species that are involved, the CH3OH, the 8COH, and the H2, right? I can look up their heats of combustion. In other words, these molecules were placed into a calorimeter and somebody determined what the delta H's were for these particular combustion reactions. So for CH3OH, in the presence of oxygen, the delta H was plus 726.6 kilojoules per mole of CH3OH. All right, so that's the left-hand side. That's the methanol. Now let's do the 8COH. 8COH, its combustion in the presence of oxygen, 1 mole of it in the presence of oxygen, yields CO2 and water, as in all combustions. Its delta H is a negative 563.46 kilojoules per mole. And finally, hydrogen. Hydrogen can be burned as well. When we combust hydrogen, we get a delta H of a negative 285.84 kilojoules per mole. So now we know the heats of combustion for all three of the species, everything that's involved, right? And again, these are given in a table that were put together by scientists who do combustion reactions in calorimeters. Now we're going to need to rearrange these three reactions, right? Just like we did with Hess's law. Now we'll leave the first one alone since it has the methanol on the left-hand side. So remember, our original reaction had the methanol on the left-hand side. This first reaction has methanol on the left-hand side. That's the only one that has methanol in it. So we're going to need to leave that one as is. So just leave that one alone. Remember, it had a delta H of a it had a delta H of a positive 726.6 kilojoules per mole, right? 726 kilojoules per mole, that's positive. So that's what the delta H will be for that first one. Now let's look at the second reaction. Here we're going to need the formaldehyde as a product. We must reverse the reaction. So we had the 8COH on the left-hand side of our combustion reaction. We need it on the right-hand side, right? So when we reverse it, we also have to reverse the sign. So it was originally a negative 563.46, but when we flip it to get the formaldehyde, the 8COH on the right-hand side, it becomes positive 563.46 kilojoules per mole. Now let's look at the last one. the third reaction. Again, we need to reverse this reaction since we need the hydrogen on the right side. So remember, in the original reaction, hydrogen was over here on the right-hand side, so we need to flip that reaction, right? We've got to turn it on the other side. So when we do that, obviously we're going to flip the sign. So the original sign was a negative, so it was negative 285.84. Now it becomes positive 285.84 because we flipped the sign. Now let's add all these together because we've got them all in the right configuration. We've got what we need in the correct positions. And so we're simply going to flip the second and third. We're going to leave the first one alone. And when we add all those together now, when we add the 726.6 kilojoules per mole, the 563.46 kilojoules per mole, and the 285.84 kilojoules per mole, we get 1,576 kilojoules per mole. And by the way, that's obviously a positive number because we're adding three positive numbers together. And so that, again, is the delta H. That is the delta H for this particular reaction. Again, 1,576 kilojoules per mole. So what have we done in this screencast? What we've done is we've used the heats of combustion for the species that were involved in a reaction to determine what the delta H was. Okay, that's a skill that you're going to need to know. That'll do it for this one. I'll see you in the next one. Thanks.